Hello, all. Good morning, afternoon, or evening. My name is Prannoy Suraneni, and it's a great honor to be presenting the Gustavo Colonnetti Medal lecture on supplementary cementitious materials reactivity from model systems to concrete. So, supplementary cementitious materials are extremely important because we need them for sustainable and durable concrete. Unfortunately, there have been lots of local and global shortfalls in the supply of the most common SCMs, which are fly ash and slag. And this has been driven by complex changing industrialization trends. So what we need to do is we need to identify, characterize, and ultimately use novel supplementary cementitious materials, and this is needed to ensure sustainable and durable concrete. So this figure, which is adapted from Scrivener et al., shows you the amounts of the most available of some of these novel SCMs. And at a global level, our solutions are calcined clays, fillers and tailings, natural pozzolans, and reclaimed fly ashes. Lots of other materials could be important at local scales. And the million-dollar question is, of course, how do we screen SCMs, or how do we measure their reactivity? Now, before we talk about how we actually do the screening, just a little bit of background on these SCMs. They can be pozzolanic, latent hydraulic, or inert, which is typically not counted as a supplementary cementitious material. So fly ash, for example, is a pozzolanic material which reacts with calcium hydroxide and water at high pH to form CSH. Slag is a latent hydraulic SCM, which it still reacts with water, but it doesn't need the calcium hydroxide. It'll react with water once it's activated to form CSH. Inert fillers don't show pozzolanic or latent hydraulic reactions, but for example, limestone shows other reactions, reactions with carboaluminate phases, for example. Now, it's really important to differentiate these three different materials because they're commonly used at very different replacement levels in concrete, and they have extremely different benefits for concrete durability. For example, ASR. So here's an example which shows AMBT expansion, which pumice is the lowest expansion, limestone is the highest, slag is somewhere in between. And this is very interestingly the exact same order of calcium hydroxide consumption of these materials. If you compare the replacement level needed to mitigate ASR for fly ash, slag, or silica fume, you'll find that it's in the order of silica fume, fly ash, and then slag. Limestone is even higher. So clearly the reactivity is quite important. So again, how do we screen or measure the reactivity? So very simply, could just using the bulk SEM chemistry work? So you see here that there is some clustering of latent hydraulic, inert, and pozzolanic materials. Is that good enough? The answer is absolutely not. The bulk chemistry does not work. It's a terrible idea to use the bulk chemistry. Consider silica fume versus quartz. They're both 95% plus SiO2. One is reactive, the other is not. And this is because it is, of course, the amorphous content which controls the reactivity. And you'll see a lot of papers in literature which say that something has more than 70% of S plus A plus F, therefore it must be reactive, but that really doesn't mean anything at all. The ASTM C618 uses the strength activity index test. This is unfortunately a pretty terrible test. It's really not measuring anything to do with reactivity. It's really measuring a filler effect because the age of testing is very early and the replacement level and the test limits are simply too low. Now, here is some data which basically shows that there's some very minor differences between reactive and inert materials, but it's really not great. Tests based on calcium hydroxide consumption, these are a lot more promising. Just that they're not accurate for latent hydraulic SCMs. But if it's only pozzolanic materials that you're interested in, these are fantastic. Now, the modified lime strength test, which has been developed by Mike Thomas and others, is really a fantastic test. The bulk resistivity is also a very nice test. These cannot distinguish pozzolanic and latent hydraulic SCMs, but they can very effectively distinguish the reactive SCMs and the inert fillers. The bulk resistivity is something that we've done a lot of work on. We've shown that especially using bulk resistivity at higher replacements and higher temperatures is very promising in differentiating inert and reactive SCMs. But also the bulk resistivity has a lot of predictive power in screening for durability. We have shown this for ASR and calcium oxychloride, but I'm not going to go into full details because of a lack of time here. Now, in general, if we think about an SCM screening test, ultimately, we are looking at the reaction of the SCM with calcium hydroxide and or water at high pH to form CSH. If an adequate, however we define adequate amount of reaction occurs, the material is an SCM, otherwise it is not. So these systems look something like this, where you have an alkaline solution, you have SCM, and you have calcium hydroxide. You can vary the mixture proportions, the solution composition, the temperature, and the pH. And you can put in cement or sand as needed. And then the reaction happens. You can measure dissolution, heat release, bound water, CH consumption, strength, bulk resistivity. These are all, of course, intimately linked, although they might not be the same thing because the reaction process is a little bit different for the pozzolanic materials and the latent hydraulic materials. Now, there's a lot of tests in literature which actually work like this. The Chappell, Frattini, R3, and modified R3 on model systems. The lime strength, SAI, other systems are on mortars, and yet there are others which run on paste and mortar. And the differentiation is, of course, important because obviously the model systems are the simplest, but in a sense, the concrete ones are the most relevant, if you know what I mean. Regardless, whichever system you choose, it's really important that, sorry about that, ideally, all of these tests that you're working on, you want them to differentiate inert, pozzolanic, and latent hydraulic SCMs, give you some estimate of strength and durability, and be rapid, robust, reliable, cheap, and simple. The test that I'll talk about for the remainder of this talk is the modified R3 test, which is something that I developed with Jason at Oregon State. So this is a variant of the original R3 test, which was developed at EPFL. Now, in this system, we have calcium hydroxide to SCM in a 3:1 ratio. It's run in a simulated pore solution, 0.5 molar potassium hydroxide, pH 13.5, liquid to solid ratio of 0.9. We run isothermal calorimetry to measure the heat release at 50 C for 10 days. And then we run thermogravimetric analysis to measure the calcium hydroxide consumption or the bound water at 10 days. Then by plotting the heat release versus the calcium hydroxide consumption, we classify the materials into inert, pozzolanic, latent hydraulic. We also get an estimate of the reactivity. Now, one of the main things that this test does differently from other tests is that it measures both the heat release and the calcium hydroxide consumption. So it's important to ask ourselves, do we need to measure both of these? I'll argue now that the answer is yes, but later on that I'll argue that maybe not. But the reason it's yes, and the reason you should measure both is that if you consider the calcium hydroxide consumption of slag and quartz, they could be similar, although these are very different materials. If you consider the heat release of a slag and a calcine clay, they could be similar, even though they are very different materials. But if you measure both the heat release and the calcium hydroxide consumption, there is absolutely no confusion. You get a very clear image of the material reactivity. And you've separated out the pozzolanic and the latent hydraulic behavior, which is really important for durability. So we've tested now well over 120 different materials, including a lot of alternative and sometimes honestly strange SCMs. And we can distinguish inert, pozzolanic, and latent hydraulic SCMs. Essentially, as you go this way, you are increasing the reactivity. And as you go this way, you're going from the more pozzolanic to latent hydraulic materials because, of course, you get here lower calcium hydroxide consumption at same levels of heat release. The boundaries are subjective. We've tried out a few different variants to separate these out, but ultimately reactivity is kind of continuous. So whatever boundaries you choose, even if you choose them in a very objective manner, they will have some level of subjectivity associated with them. We've come up with these numbers. They are kind of bound to change, but they seem to work reasonably well for the time being. One of the things that we've seen, and the reason we like this reactivity test, is that we see very strong correlations with chemical composition. Here is a correlation with the bulk CaO content. Obviously, you realize that this is limited in the sense that in reality, it's the amorphous contents that matter, but it's a nice starting point. Perhaps more interestingly, we see that the relationship between heat release and calcium hydroxide consumption, it actually depends on the chemical composition. So the slope that you get varies depending on whether the material is high SiO2, high Al2O3, or high CaO. And this is something that you can exploit because in principle, if you know the chemical composition, you only have to measure one of these parameters, and the second can be estimated from the first, right? So if you know if the material is high silicon, for example, then this calcium hydroxide consumption, you can use it to estimate a heat release. If your objective is simply screening, this is often good enough. And this can lead to a significant reduction in experimental effort and cost. So, and this is the reason I said, yeah, it's kind of important to measure both, but you can kind of get away with one if you're clever about it. Now, one of the most important points I want to make here is that reactivity is not just one point. I've been guilty of just talking about reactivity as it was, but in reality, all the results I showed so far were at 10 days, but the whole curve is important. It's not just that one point, and that's because the kinetic effects are really critical here. When you look at a class C versus class F fly ash, if you look at only the 10-day, you'll be like, oh yeah, these materials are exactly the same. But this is absolutely not true. If you look at 1 day or 3 day, these materials are very different. And this is, of course, how these materials behave in concrete, only this is an accelerated test. So early age differences are apparent in class C versus class F fly ash. Later age differences are not. And this is where you want to be very careful because you don't want to run some reactivity test, look just at 1 day data and say, hey, yeah, the class F fly ash is not reactive. The class C fly ash is much more reactive. So this is where it starts to get super misleading and super inaccurate. So we did a lot of fitting to the data that we had, the heat flow curves. And we see that in most cases, the reaction is completed by 3 days. But this is not the case for the class F fly ashes. But for other materials, you can really cut the test duration down to 3 days, significantly reducing experimental effort and cost. Different sort of corrections are needed for the class F fly ash than for the other materials. But in principle, it's possible to cut the test duration down to just 3 days. Now, one of the big issues with running this test, even though it's a great test, is that the isothermal and TGA cost $50,000 each. So can we get the same information using a cheap $5,000 furnace? And nicely enough, the answer is, yeah, it looks like we can. So what we did was, instead of using the heat release, we used the bound water as suggested by Scribner and others. So we used 100 and 350 degrees. Other measurements of bound water also exist. And from 350 to 500 in the furnace, we estimated the calcium hydroxide consumption. We see that the calcium hydroxide consumption in a furnace correlates pretty nicely with the calcium hydroxide consumption in a TGA. The bound water in a furnace correlates pretty nicely with the calcium hydroxide in a furnace. There are some outliers here, the slags, for example, and there are also some outliers here. There's no such thing as a free lunch, right? If you're saving 95% of your cost, you will lose some fidelity in your data. But ultimately, if your objective is really just to do screening, then I think that these results are extremely promising. In principle, the 3-day cheap reactivity test holds a lot of promise for both standards and for specifications. Now, we've talked a little bit about bulk chemical composition, but really reactivity depends so strongly on fineness and amorphous content, which we really haven't talked about in enough detail. So I have here this extremely complicated graph, which shows that, well, the reactivity fineness relationships are extremely complex. So for two different materials, for pumice and ground glass, we see that this slope is quite gentle. As you go from about 10 microns to 120 microns, the materials go from reactive to inert. And these are materials which are high amorphous content, subjected to low energy grinding. On the other hand, these mine tailings, in a short change of about 10 microns or so, they go from inert to reactive. And that's because these are low amorphous content materials, but subject to high energy grinding. So there's different amorphization happening here compared to this case. Differently, you see that the limestone, the change in D50 doesn't actually do anything. It's still completely inert. And of course, the change in fineness in the limestone will affect concrete properties. We are just talking about the pozzolanic or latent hydraulic reactivity. So here we are really seeing that there are lots of different reactivity fineness relationships, but the fact is, because they're so different and they depend on the amorphous content or the grinding, you can actually tune them, especially using grinding aids, for example, to develop ideal reactivity fineness relationships. And this is something that we are working on. Clearly, it shows here that the inert tailings, could be amorphized, activated at increasing fineness levels. Now, we come to a completely different process that happens if instead of grinding, you actually sieve the materials. So for three different fly ashes, we separated out the 20 micron fraction and the 45 micron fraction. And for this fly ash, there's a 3x, it's closer to a 2x difference in reactivity. For this one, it's a 3x difference in reactivity. And for this fly ash, it doesn't matter at all. So for this fly ash, what we see is that as you change from the 20 micron to the 45 micron fraction, the fly ash goes from a class F fly ash to a class C fly ash. The composition completely changes. But at the same time, this is also a very strange fly ash because it has a large, very porous, it's an unconventional fly ash, large, very porous particles. So the fineness surface area is completely different. Fineness surface area relationship is completely different than for the other fly ashes. That's why you get this different relationship. So all of this is great, but can we predict paste or mortar or concrete properties? And the answer is it depends. Yes, we can, but there are a lot of other properties that are important as well. For example, at early ages, we can't predict anything because reactivity is not really important at such early ages. Ditto with low SEM replacement levels. But at later ages and relatively high SEM replacement levels, we find that we can predict the bulk resistivity or the strength evolution based on reactivity. And we've shown such correlations for paste, mortar, and concrete. This is great because it suggests the fundamental importance of reactivity tests. But I have to emphasize here, there are a lot of other factors that are important. You can't use only reactivity to predict strength. And the reason for that is, for example, we tested the strength development with three different slags here. The most reactive slag gives the lowest strength. And that's because this slag has meionite, which reacts just fine in a reactivity test. But unfortunately, if you put it in a cement paste, it will mess up your aluminate silicate balance. So it doesn't actually lead to very much strength. So reactivity is important, but the other factors have to be considered as well. You simply cannot just say, oh, this is a reactive material, this is going to give you this much amount of strength. You can for many materials, but not for all materials. There are a few other factors that you need to take into account, corrections that you need to make, etc. But generally, we show pretty nice correlations. A similar situation happens when we talk about concrete durability. We've shown that the modified R3 test can be used really for fantastic screening of SEMs, both for ASR expansion and for calcium oxychloride durability. So specifically, you can you can separate out materials into unlikely to mitigate, possible to mitigate, and likely to mitigate, both for ASR and for calcium oxychloride. The replacement level starts to become quite important as well, because a lot of the mitigation here is served simply by replacing the cement. But what we see is that, if you're classifying it as unlikely to mitigate, yeah, it's not really going to work. You don't have to run any further testing on it. So, you've screened it out right there. For the complete K-oxy mitigation, it will most likely work unless there's really something weird going on. But for the mitigation possible, here you need to do further testing, because the amount of alumina, the amount of alkali, or various other factors can actually dominate over reactivity. But either way, reactivity can serve as an extremely rapid starting point to say, oh, you know what, this material is really worth it to study durability, or not really. So with that, I'd like to conclude my presentation. The most important conclusions that we see is the modified R3 is really an important method. You can use it to differentiate inert materials, pozzolanic and latent hydraulic SEMs. You can get a measure of reactivity. And really getting two measures, the heat release and the calcium hydroxide consumption, is probably the way to go. But you can estimate one from the other if need be. This test, normally the way we are running it is quite expensive, but you can cut it down to 3 days, and it can be performed using a $5,000 furnace if you are okay with just using it for screening. Reactivity fineness relationships are complex, potentially tunable, and you could manipulate these relationships in a lot of different ways. The reactivity can be linked to paste properties, ASR expansion, oxychloride durability, and the modified R3 test can be used to screen SEMs for durability, but a lot of other factors are important in this durability or paste property evaluation. So I want to thank my sponsors, without whom this research would not have been done. So I have a list of them here. I won't read through everything. And really, there are too many people to thank for where I am right now. But the folks at IITM for getting me interested in cement and concrete in the first place. Everyone else at UIUC. So without you guys, I would not have continued on my path to actually do a PhD. So Manu Santanam, Ravindra Gettu, Leslie Struble, John Popovich, thank you very much. Robert Flatt, everyone else at ET and Zurich, because you guys were the best PhD group that I could ever have wished for. Jason Weiss, Berkaneshko, Jason Eidecker, and others at Oregon State University for making me sure that an assistant professor is what I wanted to do while I was doing my postdoc. My colleagues at University of Miami for making it a great place to work at. A lot of my bachelor's, master's, and PhD students and postdocs that I worked with over the last 14 years. I can't mention everyone, but I will mention Shivakumar Ramanathan, Nima Husseinzadeh, and Ying Wang, who contributed tremendously to the work shown here. And finally, collaborators all over the world for really making this an awesome working experience. Thank you very much also to the audience for your patience. And finally, I want to thank Mom, Dad, and my wife, Swati, without whom I would definitely not be doing any research. So thank you very much.